Good morning, viewers. Today's video lesson on cantilever beam with uniformly distributed loads. In the previous lesson, we have gone through cantilever beam with point loads. When we take a cantilever beam, it will have two ends. One is a free end and the other one is a fixed end. If we have a load at a free end, like W, what will be the shear force and bending moment diagrams for that. And also we have taken up not only a single point load, but multiple point loads at various sections of the beam. Then what will be the shear force and bending moments we have seen in the last video lesson. In today's video lesson, we will be talking about a cantilever beam is subjected to a uniformly distributed load. Uniformly distributed load means a load which will be carried entire span uniformly or some part of the span, but whatever the load is there, the load will be equal in all directions to that effect. So that is called uniformly distributed load. So in this video lesson, we will be talking about a cantilever beam subjected to uniformly distributed load, and what will be the shear force and bending moment diagram, how to draw shear force and bending moment diagrams for that. So in order to draw shear force and bending moment diagrams for this cantilever beam, which is subjected to UDL, first of all, we have to calculate shear forces and bending moments at the various sections of that beam. So that is what we have to do. So let us go with today's. First of all, we will take the entire span, then we will take a part of span, and we will try to do one numerical problem on that. So here we go. I would like to share, I have prepared a PPT for this, and I would like to share that PPT. So shear force and bending moment of cantilever beams. This video lesson is especially for the type of load is UDL, that is uniformly distributed load. I am Anand Padavala, senior faculty member in Department of Technical Education, Government of Telangana. So especially this video lesson is useful for diploma as well as engineering graduates of mechanical as well as civil engineering students. Hope you will enjoy this lesson. So we have seen what is a cantilever beam. Just now I said cantilever beam will be having two ends. One is a fixed end, the other one is a free end. So at the fixed end it will be fixed and the other end is free. So to give a proper definition for cantilever beam, a cantilever is a rigid structural element which extends horizontally and is supported at only one end. So typically extends from a flat or a vertical surface such as wall to which it must be firmly attached. So this end should be firmly attached or fixed, the other end will be free. It's a structural element. So when we have we can place any load on this element. So we have seen some practical examples of cantilever beam in the last video lesson. Same thing for a recap purpose. I mean, this is a cantilever beam. See, we have a fixed beam here. And here we have a what we call it as here a car shed or a vehicle shed. So you have a cantilever beam here. So we have seen in the last class cantilever beam with a point load at free end. So bending moment and shear force diagrams are given below both. So when point load is there, so what will be the net resultant, I mean shear force at any section between A and B, it will be W only. That's why it is no load between them. Therefore, it follows it's a constant load, a constant shear force load. Therefore, so it will act for the entire span. Now, if you take a bending moment diagram, it depends on the distance from the free end. So, for example, I want a section here. How much distance it is? So it will be W into X. Therefore, W into L at this end. This is the bending moment diagram. We have seen some problems on this also in the last video session. Now, today we are talking about cantilever beam with UDL over entire length. We have seen what is UDL. UDL is nothing but uniformly distributed load for the entire length. See here. For example, this is AB is consider a cantilever beam AB of length L fixed at A and free end at B. This is length. The length is L. Now, let this cantilever beam is carrying a uniformly distributed load and the load is W per unit length. For example, if you take L meters, so the entire span is there. Therefore, small w into L will be the total load. Therefore, this is uniformly distributed load generally indicated with the per unit length, because now it depends on the length of a span it is spreaded over. No. So cantilever beam with UDL, how to calculate shear forces and bending moment diagrams. So in order to calculate shear forces and bending moment diagrams, first of all, we have to calculate, in order to draw shear force and bending moment diagrams, we have to calculate shear forces and bending moments at various sections of the beam. So shear force, consider a section X at a distance X from free end. So I'm taking a section X here, capital X. This section or a point on this beam is at a distance of X from free end. So it is a X from free end. Let us consider. So let us say that Fx is a shear force at this section. Fx is a shear force at this section. And let Mx will be the bending moment at this section. So let us, now we have to find out Fx and Mx for any section. So what is the definition of a shear force at any section? So if you want to calculate shear force at any section, it is nothing but the resultant force acting on right or left portion of that section. For example, we have taken this uniformly distributed load of cantilever beam A and B. If at all we want to find out shear force at any section, for example, we want to find out the shear force at X. So in order to find out the shear force at this section, what we have to do is we have to consider either right side of this section or left side of this section. So if we, let us take a right side or left side, depends on the circumstances. So but any one portion we have to take. And suppose if I have taken a right section, in this right section, the total resultant force acting on this section will be the shear force. So how much force is applied here, resultant force? That means how much load is there in the center, net load, that is resultant load in this section will be the shear force of at this section. Now consider the right portion of the section X. Is we have to consider this right portion of the section. That is right portion means from X to B, capital X to B. The resultant force acting on the right portion of the section X is nothing but it is equal to how much load it is there. So the span is here small x. So the load here is W per unit length. So small w into the length will be the total force acting in this right section. So we have only UDL, no reaction forces at this moment. So only we have UDL. So when we have UDL, what we have to do is we have to multiply the magnitude of the UDL per unit length into the span of the spread of this UDL, uniformly distributed. Therefore, W into length of the right portion, that is therefore hence shear force at X is nothing but Fx equal to plus W into X. Why we have taken plus symbol? Plus symbol because when we have a right section, when it is acting downward direction, then we have to consider it as a positive. In the sign conventions, in the very starting lesson, we have seen how to take sign conventions. Sign conventions taken as far as shear force are concerned. If we consider the right section, if downward direction is the resultant force, then we have to take it as a positive. And if we take a left hand side, when it is upward direction, then we have to take it as a positive. So these are the things. And moreover, so the resultant force, the direction of the resultant force here is downward. That's why we have taken plus signal. Therefore, shear force at X equal to Fx equal to plus W into X. So clearly it says that shear force will follow straight line law. Why it is straight line law? We know that the law of straight line is y equal to mx plus c, or it directly mx we can take. It is directly proportional to the distance x from the free end. Therefore, it follows straight line law. That's why whenever we draw a shear force for cantilever beam with UDL, when UDL is there, we have to draw a straight line passing from this point to the next point. Therefore, we know that Fx, that is shear force at section X, is equal to plus Wx. Now, we will find out the shear forces at various sections. For example, if you take at B, if at all we want to find the shear force at B, now we know that at B means X value is 0. So X value is 0, then for shear force at B will be 0 because W into 0 is 0. Therefore, shear force at B equal to 0. Now at midpoint, for example, let us say that some midpoint. Midpoint, the length is L by 2. L by 2. Therefore, shear force at that midpoint will be W into X. X is L by 2. Therefore, plus W L by 2. Now, shear force at A, if at all we want to find out, what we have to do? Shear force at A is nothing but X equal to L. Therefore, this is the distance from free end we have to take. Free end is B. From B we have to take. This is X equal to L. Therefore, shear force equal to W into X. X means here it is L. So, W into L. Therefore, this is what a shear force. So, clearly, hence, shear force is proportional to the distance from free end, that is X. It is clearly the shear force is proportional to the distance from free end. If the distance is 0, shear force is 0. If distance is L, the shear force will be W into L. Now, how the shear force diagram will be? It will be like this. For example, this is a load diagram and this is shear force diagram. We have seen while calculating shear force at B is 0, shear force at X equal to Wx, and shear force at IA equal to WL. And we said that it follows a straight line law. Therefore, what we have to do? From B to X, we have to draw a straight line. From X to C, we have to draw a straight line. So this entire thing will be straight line. So this will be L, shear force. And this is the baseline. And positive sign indicates that it is making a net shear force. in a positive direction. That is, it is, if we take a right hand side direction, it should act downwards. So this is what a shear force diagram. Now, how to calculate a bending moment, how to draw a bending moment diagram for the same cantilever beam with UDL over entire length, we will see now. So bending moment diagram. So this is what the same section. So now bending moment at any section. We know the definition of a bending moment at a section is nothing but algebraic sum of moments of forces acting on either side of the section. For example, if you take two sections here, I want to find out two portions of the section, right hand side and the left hand side. In the right hand side, if we consider, we have to find out the algebraic sum of the moments of forces. That means whatever the forces are there here, the total moments that these forces will make about this point is called the algebraic sum. That means net moment which is acting on either side, either you take a right side or a left side. So that is called bending moment at any section. Now, to calculate bending moment of a UDL over a section, it is converted into point load acting at a CG. We know that we have to calculate. So this entire span is with uniformly distributed load. So how many loads, point loads we have? Point load, if point load is there, we can easily calculate how many point loads are there. Those many point loads into the distance from this place, we can easily find out the bending moment. But here the load is spanned over the entire thing. If you take right section from X to B, that the UDL is spreaded over. Therefore, it is very important thing to be noted down here is, whenever we calculate bending moment of a UDL over a section, what we have to do is we have to convert this UDL into point load. So what will be the equivalent load to this UDL? So W is a per unit length, small w, into X. Therefore, total load is W into X for this entire span. That is the total load. If at all we want to replace this uniformly distributed with a point load, that is equivalent to W into X. That will be the point load. We know that the point load, but where it will be acting? This will be acting at the center of gravity of this section. What will be the center of gravity of this section XB? The midpoint of XB will be the center of gravity. Therefore, we have to replace the UDL into a point load, and we have to give a place that the midpoint of the span of that section should be taken as a point of load. Therefore, this is very important concept when we are calculating UDL, bending moment for a cantilever beam with a UDL. So this is what we have. Therefore, consider a right side of a section. As usual, we are considering right hand side of section. Now, BM at X, that means at this point. How to calculate? It is nothing but mx equal to minus y minus as sign we have taken. I will come in little moment. So this is nothing but total load on the right portion. What will be the total load on the right portion? It is small w into X is the total load into the distance of CG of the portion from X. That means where it is acting at the center of gravity. That is, center of gravity means exactly at this portion. So what will be the distance of this center of gravity from capital X is the distance. So the total load into this distance will be given the bending moment, and it is indicated with the negative signs. Why is indicated with the negative signs? If you observe, this is a cantilever beam, for example, and it is a free end. When a load is applied, it is making a hogging, that is a convex shape. So whenever a convex shape is there, we have to take it as a negative. When we take a concave like this, if we take, then we have to take positive. These are the sign conventions. In the very first lesson, we have discussed about this one. So whenever a bending moment like this, we have to take it as a negative. When we have a concave, we have to take it as positive. That means this is arguing. Moreover, if you observe, it is this load is making a movement of a clockwise direction. That means this is the clockwise direction. Whenever we are making a clockwise direction, what we have to do is we have to take a, when the right side direction, clockwise movement, then we have to take it as a negative. Right hand side direction, anti-clockwise, right hand side section, anti-clockwise direction, we have to take it as a positive. So here this load is making a clockwise direction of movement about this section, therefore we have to take it as a minus sign. Therefore bending moment at x is nothing but total load on the right portion into distance of CG of the portion from x. If we consider the left portion, then we have to take the total load and the displacement, the center of gravity of this load from this section we have to take. Now, therefore, clearly, bending moment at x is nothing but total load, as I said, W into x. And what is the center of gravity? Exactly at the center of this xb. And what will be the distance from x to b? It is x small x. So from x to b at the midpoint will be x by 2. So therefore minus wx into x by 2. This is nothing but minus wx square by 2. So if you want to take any section between b and a, the formula here is bending moment is nothing but minus wx square by 2. X is the distance of that section from free end. So this is, we have to remember minus wx square by 2. Otherwise also we can calculate. And as I said, negative sign is due to clockwise direction of the movement. We know that mx equal to minus 0. Now let us try to find out the bending moment at various points. Let us try to find out bending moment at B, bending moment at the midpoint, bending moment at the section A. So whenever we are calculating bending moment at B, what is the x value? That is distance from free end. B is nothing but a free end. Therefore, x value at B is 0. Therefore, what we have to do is we have to substitute in this formula mx equal to minus wx square by 2. When x equal to 0, therefore bending moment at B will be 0. Because x equal to 0, therefore if you substitute 0 value here, the bending moment will become 0. So the bending moment at B, that is at free end of a uniformly distributed loaded, when it is spreaded the entire span, it will be 0. Now, what is the bending moment at midpoint? So midpoint is nothing but x value will become L by 2 because exactly at the center of AB. Therefore, what we have to do is x equal to L by 2. Therefore, bending moment is equal to W into L by 2 because x value is W by L by 2 and x by 2 here instead of L by 2 by 2. Therefore, at the midpoint bending moment will be minus WL square by 8 will be the at midpoint. Now, what will be the bending moment at x equal to L, that is at A, x value L. Therefore, we have to substitute in this formula. Bending moment at A is nothing but minus W into, instead of x, what we have to put? L square by 2. Therefore, bending moment at B equal to 0, bending moment at A equal to minus WL square by 2, and bending moment at midpoint equal to minus WL square by 8. clearly, if we see, bending moment at any section is proportional. So bending moment at any section between A and B, from this formula we can clearly understand that it is proportional to the square of the distance, because W is constant here. W won't be changed. Only changing parameter is X. When the distance changes, that is the section distance changes, then the bending moment varies. So it varies to it is proportional to the square of the distance from the section from free end. From free end, how much distance the section is, that is. So clearly it is proportional to the square of the, therefore it follows parabolic law. Therefore, whenever we draw a bending moment diagram for a cantilever beam with UDL for over entire length or any length, whenever the span is there, so what we have to do is, whenever we are drawing a bending moment diagram, we have to see that the bending moment diagram is in parabolic shape, so that from one point to the other point, when the span is there, we have to draw bending moment in a parabolic line. Why parabolic line? Because it is proportional to the square of the distance of the section from free end. This is what we have. Y equal to cx square is a law of parabola. Therefore, like that we can calculate. Now, bending moment diagram. So this is what bending moment diagram. This is shear. This is load diagram. This is shear force diagram. This is bending moment diagram. If you observe shear force diagram, above the baseline it will be there because it's positive. For shear force bending moment diagram, below the baseline because it's negative quantity. So bending moment at B is 0. Bending moment at section X equal to Wx square by 2, and bending moment at L equal to WL square by 2, and bending moment at the midpoint, it is not shown here, but if at all we want to calculate at the midpoint, it equal to WL square by 8, and it will be in the clockwise direction, that is we have to take as a negative sign. This is a shear force and bending moment diagrams for a uniformly distributed load over a cantilever beam spread over the entire span of the cantilever beam. So this is what we have. Now let us try to understand the concept of shear force and bending moment diagrams of a uniformly distributed load of a cantilever beam by taking a numerical problem. And in this numerical problem, we are not taking the entire span, because for the entire span we have seen and we have derived the formula also. Simply by substituting the values of small w and small x values and L values, we can easily find out the bending moment and shear forces at various sections, and thereby we can find out we can draw the shear force and bending moment. That's why I'm not taking the entire span. In this numerical, I'm taking a problem. Let us see the problem first. Numerical problem on cantilever beam with UDL. Here is a problem. A cantilever of length 2 meter carries a uniformly distributed load of 1 kilonewton meter run over a length of 1.5 meters from free end. See, observe here, the length of the cantilever is 2 meters, whereas uniformly distributed at UDL, that is 1 kilonewton per meter. That means W value is 1 kilonewton per meter. And this UDL is not spread for the entire length of 2 meters. It is spread over only for a length of 1.5 meters from free end. So from free end. So in this question, they are asking to draw the shear forces and bending moment diagram for this beam. So whenever the problem is given, what we have to do is, first of all, we have to draw the load diagram. Here the load diagram is not given. So whenever they don't give a load diagram, when they give the description, so it is our primary duty to draw the load diagram first. So in order to draw the load diagram, first of all, we have to take solution, load diagram. So first of all, we have to draw the cantilever beam of length 2 meters. So here it is a cantilever beam, that is A and B, and its length is 2 meters. So now above that we have to draw the load. We have to add the load. So what kind of load we have? Uniformly distributed load. And it is not for the entire span. It is a span from 1.5 meters from B, that is from free end. So I think from up to this it will come 1.5. Let us see. So we will add the load for this. So here we have added the load. So it is 1 kilonewton meter run. That means per meter run. That means 1.5 meters. This is. So BC, CB is the length of the UDL, that is 1.5 meters. And the magnitude of the UDL is 1 kilonewton per meter length of the span. This is what we have. So this is the load diagram we have seen. Now we have to see the given data. What is given? Length of the cantilever L equal to 2 meters and UDL equal W equal to 1 kilonewton per meter, and the length of the UDL is 1.5 meter. The length of the UDL is 1.5 meter. So if at all we want to convert this entire UDL into a point load or a total load, then the total load W, capital W, will become the magnitude of the UDL, that is 1 kilonewton per meter, into the total length of the UDL, that is 1.5 meters. So 1 kilonewton per meter into 1.5 meters will give rise to 1.5 kilonewtons of load, that the UDL. So UDL, when if we replace with a point load, the value of that point load will be 1.5 kilonewtons. And the conversion of the UDL into point load is very much important when we calculate bending moment diagrams at various sections. Now, we will try to find out shear forces at various sections. Now, consider any section X between C and B. See, between C and B, let us consider. This entire span consists of two portions. One is A and C and C and B. C and B is the portion where UDL is there, and between A and C there is no load at all. If we observe from A and C, no load. From C to B you have UDL. These are the two different sections of that beam. Now first consider the C and B, any section from C and B. For example, I have taken any section X here, and if the distance from free end is small x, then how to calculate shear force at a section? So shear force at that section will be, we have seen that formula, that the distance, the magnitude of the UDL into the distance from free end where the section lies. Therefore, Fx equal to small w into x, where small w is 1 kilonewton per meter and x is the distance of that section, any section between C and B from free end. Therefore, suppose you want to find out the shear force at B. Therefore, shear force at B is W value is 1, whereas X value will be 0 because it itself is a free end. The distance between free end to free end, that for same end, is 0. Therefore, shear force at B is 0. Now, shear force at C, if at all we want to find out, what you have to find out? So, the X value here will be 1.5. So, 1 into 1.5 equal to 1.5 kilonewtons. Now, if at all you want to find out the shear force at A, now if you observe to the right section, only one load is there, that is UDL. So whatever the shear force here, the same shear force will continue up to A, because there is no load between A and C. When there is no load between A and C, whatever the shear force at C will be equivalent to shear force at A, because it's a constant shear force between A and C, because there is no load between A and C. Therefore, the shear force at A is equal to 1.5 kilonewtons. Therefore, it is clearly shear force at B is 0, shear force at C is 1.5, and shear force at A is equal to 1.5 kN. Clearly, we know that the shear force follows a straight line law between C and B. Between C and B, it is a straight line law because it depends on the distance from free end, a section. That's why it's a straight line law. Between A and C, there is no force. That's why no load is there. Therefore, shear force will remain constant. Therefore, whenever we draw a shear force between A and C, it should be constant shear force. That means shear force follows a parallel line to the load line. So hence between A and C, that is shear force represented by a horizontal line. Now we will try to draw a shear force diagram for the given problem. Now the shear force, this is a load diagram. Now the shear force diagram is like this. It is clearly indicating that shear force at B equal to 0, shear force at C equal to 1.5, and shear force at A is also 1.5, and it follows as far as UDL is there. For this UDL, it varies with length. Therefore, from 0 to 1.5 kilonewtons shear force, we have to draw we have to join these 2 points with a straight line. Here you have a horizontal line because there is no load. The same load will be, shear force will be here. Therefore, from D to E, you have a horizontal line. So this gives the shear force diagram, and it is indicated with positive sign because it is, for right section we are taking download force is taken as a positive. This is what a shear force diagram. Now let us try to draw the bending moment diagram for the given numerical problem. So when we calculate the bending moment, the same system we have to adopt here. What we have to do is, so we have to adopt, we have to divide this entire span into 2 sections. One is section between B and C, that is where the UDL is there, and between C and A, where there is no load at all. So we will try to find out the bending moments between any section between A, B and C. Suppose if you take any section which is X distance from B, we will try to find the bending moment, that one. If we substitute X equal to 0, you can calculate bending moment at B. If we substitute X equal to 1.5, we can calculate the bending moment at C. And after that, we will try to find out a bending moment between A and C. Then there is no load between them. So we will take any section between A and C and let the distance of this section from the free end B is Y, and this let the section be Y. So the distance also from free end is Y. Then we will try to find out the bending moment at this section. Then if we can calculate Y equal to 1.5, we can get bending moment at C. And when Y equal to 2 meters, then we can calculate the bending moment at A. So 2 parts, we are dividing the bending moment, calculations of bending moment into 2 parts. So first part is any section between B and C. Now consider any section X between C and B. Now let the distance of this section, any section X from free end B is small x. Let's its distance. So therefore, bending moment at this section, how to calculate? We have seen the fundamentals in the in this lesson only, how to calculate. So whenever we are talking about bending moment of UDL, what we have to do is, we have seen that we have to convert whatever the right hand side of the section is there, that entire section we have to convert that load into a point load, and the point of application of that load also we have to calculate. From there we have to find out the bending moment. That's what we have seen. Now how to calculate? We have seen mx is the bending moment at x, is nothing but, so for example, take any x, for example, x from this place to this place is x. Therefore, the load, the entire load from this place to this place is small w into x is the load. And where this load will act exactly at the center of gravity of this section. For example, from here to here is xb. So where it will act? It will act at a midpoint of xb, that is from this point. So from this place to this place, if it is x, then the midpoint of it will be x by 2. Therefore, the bending moment at x is nothing but minus wx into x by 2, that is minus w x square by 2. As we have seen that this bending moment is making a hogging or a convex shape of bending at the top layer. Therefore, when a convex shape is there, we have to take it as a negative. When is a concave is there, we have to take it as a positive. And also, it is making this load will making a clockwise direction. Whenever a clockwise direction movement is there about this section, then this clockwise direction in the right portion of the section, we have to take it as a negative sign. So hogging will be taken as a negative sign. So here W value is 1 in this given problem. Therefore, Mx at any section between C and B is nothing but it depends on the square of the distance from free end, that is minus x square by 2. So clearly it is given that it follows from between C and B, it follows parabolic law because it is directly proportional to the square of the distance from free end. So mx equal to minus x square by 2. Now let us try to find out the bending moments at various sections at B and C. So if at all we want to find out the bending moment at B, what we have to do is we have to substitute x value as 0 because here it is x value is 0. So at x equal to 0, that is B at B, bending moment at B equal to minus 0 square by 2. Substituting in this formula, in x place we have to substitute 0. So 0 square by 2 equal to 0. Now bending moment at C, that means at the end of this section, at the end of this UDL, that is equal to x equal to value is 1.5. Therefore, bending moment at C equal to minus 1.5 square by 2. That is nothing but we have to substitute x value is 1.5. That when we calculate, it will when multiply 1.5 into 1.5 by 2, the value is minus 1.125 kilonewton meter. Kilonewton meters because the load is given in kilonewton and the distance is given in meters. Therefore, the bending moment will be minus 1.125 kilonewton meters. So clearly, Bm varies according to the law of Bm varies according to parabolic law between C and B. C and B, the bending moment varies according to the parabolic law because it is directly proportional to the square of distance from free end of the section. Now, consider any section between A and C. Now, we have seen this section. Now, we will try to find out any section between A and C. Let us the section is capital Y between A and C. And if the distance Y is from free end, that means I have taken a section here and let the distance of this section is from free end B is Y. That means here to here it is small y. Now, the total load of the UDL, if you observe clearly between A and C, no load. But this load will make a movement on this section. Therefore, what is the total load of this UDL is UDL into the span, that is span is CB. So 1 into 1.5 kilonewtons is the total load. And where it will act, and this act at the center of gravity of CB. So what is the center of gravity of CB? It is midpoint. What is the midpoint? The total length is 1.5 meters. Therefore, midpoint is 0.75 from free end. From free end or from C end also. So it is from freehand. So now I want to find out bending moment at any section Y between A and C. So between A and C, if at all I want to find out the bending moment, so how to find out? It's a total load into distance between section and CG and CB. Suppose this is the center of gravity of the CB and this is the section. From this section to this CB is the distance. And the distance into the total load, that is 1.5, will be the bending moment on this section. And negative sign, as I said, negative sign because it is making a hogging. That is, this is making this type of bending moment, that is hogging. Therefore, minus sign is given here. Therefore, clearly, it is total load is 1.5 into distance between CG and CB. That is distance between the section from this place, CG of CB is 0.75. So from this portion to this portion is Y, and this portion to this portion is 0.75. Therefore, the distance between this portion to this portion will be Y minus 0.75. So here we have. So let us try to find out bending moment at C and bending moment at A. That means section between A and C, if at all. Already we have found out the bending moment at C in the previous section, that is between C and B. But now we will calculate the bending moment at C with the help of this new section, and both should be equal. Let us see. So at C, that means at C, Y value, what is Y value? That is the distance from this place to from free end. It is 1.5. Therefore, bending moment is, if we substitute Y value as 1.5 here, minus 1.5 into 1.5 minus 0.75. When we calculate, it comes exactly as we have calculated earlier. That is minus 1.125 kilonewton meter, and minus sign is because of hogging or convexity at the top of the bar or beam. Now let us find out the bending moment at A. The bending moment at A, that means the A point is at 2 meters from B. Therefore, Y value is 2 here. Therefore, bending moment at E is nothing but 1.5 into 2 minus 0.75. That is nothing but 1.5 into 1.25 minus, that is nothing but minus 1.875 kilonewton meter. Clearly, if you see, it varies. That bending moment varies with Y. That is distance from free end. That means it follows a straight line law of straight line between A and C. Therefore, between C and B, it is parabolic law, bending moment. Between A and C, it is straight line. And these things we have to remember when we draw bending moment diagram. Now, let us try to draw the bending moment. This is a load diagram, and this is the bending moment diagram. See, bending moment diagram. Bending moment at B is 0. Bending moment at C is minus 1.125. Bending moment at A is 1.75. If you observe, when we join C and B, it should be parabolic shape because it follows parabolic law, because it is directly proportional to the square from the distance of free end. That is parabolic. And at section A, it is 1.875. And when we draw a line, when we join line from C dash to A dash, we have to draw a straight line. So this line should be a straight line and this line should be a parabolic line. So this is how we have to draw a bending moment. So whenever we draw shear force and bending moment, it is a good practice that all these three things, the diagrams will be at one place. That is first load diagram, followed by shear force diagram, followed by bending moment diagram. So it will be like this. This is a load diagram, the shear force diagram, and bending moment diagram. And all these points should coincide. A point, C points, and B points. This is what we have. So this is what we have. So I think you have understood some of the concepts of a cantilever, shear force and bending moment diagrams of a cantilever beam with a uniformly distributed load, whether it is an entire span or a part of a span, how to calculate we have seen. So hope you have understood these concepts. If you like it, please share this channel, subscribe this channel, and please share with your friends. Thank you very much for watching this video.